Hello everyone. I decided to record this tutorial because I wanted to go over typical mistakes which some of you or even many of you committed on test 1. And the majority of these mistakes were related to question 2, which is about finding eigenvalues and eigenvectors of 3 by 3 matrix. So the main drawback was that you were not able to realize that you were making mistake already. And so, for example, some of you made a mistake in the very beginning. You didn't calculate lambdas, eigenvalues correctly, but you didn't notice that, and you pushed on. And as a result, the whole question 2, even though it was so long and so big, turned out to be incorrect. So now I'm going to go over these examples of finding eigenvalues for both matrices 2 by 2 and 3 by 3, but the emphasis will be put on the technique of how to check your results on the fly while you are doing lambdas one by one and the eigenvectors one by one, and also how to detect your mistakes. I think it's a very useful technique, and you will still have a chance to come across a similar problem during your exam, which is in June. So I hope, hopefully, this video will be helpful for everyone. Okay, let's start. So the first example, I'm going to give you only two examples during this session. Oh, I don't know about, is it good? No, my image is not good. Okay, we need to make some improvements. Looks much nicer this time. Not so blurry anymore. So the first example will be about matrix 1 by 1, 2 by 2, sorry. So this is actually question 1b from tutorial 2, I suppose. It doesn't matter where it's from. I can't reveal you the tests, the problems given to you during the test, but it doesn't matter actually. The main thing is here. Okay, so it's question 1b from tutorial 2, I suppose. Yeah. In this tutorial, you are given you are given matrix for 1, 3, 2, and you are asked to calculate eigenvalues as usual and eigenvectors. As far as I can remember, in tutorial 2, you were not familiar with the concepts of model and spectral metrics, which are actually not difficult issues. But so let's concentrate on lambdas and on eigenvectors especially. Okay, so you all know how to calculate eigenvalues. It's just a piece of cake actually. So 4 minus lambda 1, 3. You need to subtract lambdas from diagonal elements and set up this determinant to 0. And then it's time to solve this equation. So let's calculate this determinant, nothing fancy here. And now we do this multiplication, lambda squared minus, I suppose, 6 lambda plus 8 minus 3 will be plus 5. I think it's correct. So this is a quadratic equation, but as this is a super easy, super simple quadratic equation, sometimes it's very easy to guess its factorization. This is my favorite method. I would recommend it to you if you don't quite like it. If you're more used to the formula with this discriminant, and so you'd better use this formula. It's just my favorite technique. Okay, so as a result, you have two lambdas here. Lambda 1 is equal to 1, and lambda 2 is equal to 5. Okay, so what happens next? The next assignment for you is to calculate eigenvectors corresponding to each of these lambdas. Or we can even divide our page into two columns. So let's discuss lambda 1 is equal to 1 here, and lambda 2 is equal to 5 will be discussed here. So how can we find these eigenvectors? You know that you need to take this matrix, which is already here. Maybe we should put a red frame around it. And you need to substitute your current lambda. So in this case, it will be 1. So let's look at this matrix, and we rewrite it as a matrix now. 4 minus 1 will be 3, 1, 3, and here we have 2 minus 1, it will be 1. And now you need to solve this equation. Actually, you need to solve the system of equations, x1, x2, is equal to 0, 0, and so on. But some people who has done this task many times, they try to omit this. They immediately start dealing with this matrix. So maybe in the future, in my future examples, I'm not going to write this again. So what is the indication? So remember that the topic, the objective of this tutorial, of this video, is to teach you how to detect your errors, which are inevitable actually. Maybe I already committed error here, who knows. So the indication is, in the case of 2 by 2, these two rows which are in this matrix, they should be proportional or sometimes even equal. As you can see, the first row is absolutely the same as second row. This is a good sign. It means that so far you haven't done any mistakes. So let's push on. So what do we need to do? Secondly, we need to rewrite the remaining row as an equation. 3x1 plus x2 is equal to 0. Then maybe it's much more convenient to rewrite it like this, minus 3x1. And in this case, it will be super easy to find the pair of integers x1, x2 who satisfy this equation. So for example, if we set up x1 to 1, we immediately get that x2 will be equal to minus 3. So that's how you did it, and nothing new for you here, and so on. But the question arises, is it possible to check this result? So for example, of course, we made sure that our lambda is similarly correct because these rows are proportional. This is the indication. But you could easily make a mistake here. And by the way, some of you did make a mistake when calculating these eigenvectors. For example, some people swapped the places. Instead of 1 minus 3, they wrote something like 3 minus 1, or just swapped the order. So how to check this result? It actually, this is my habit to always check my results. So I'm going to reveal this now. You know what? You need to recall the definition of eigenvectors. What is eigenvector? Let's recall it. Definition. So eigenvector, let's spend some time. Eigenvector of matrix A is a non-zero vector. Non-zero, by the way, non-zero. It was another type of mistakes many of you did on the test. Non-zero vector, I don't know, E. I missed one phrase. Eigenvector corresponding to lambda, to eigenvector value, is a non-zero vector which satisfies the equation. So if you multiply matrix A by this vector, by this eigenvector, it will be the same as you multiply lambda by this vector. So this is a very important definition. And you can exploit this definition actually to check your result. Why not? So in our case, you need to, so we have vector E1 corresponding to lambda 1 is equal to 1. So our equation should look like this. If I multiply my initial matrix A by this vector, it's the same as multiplying this vector by 1, by lambda equal 1. I put a question mark here because I'm going to check this equation, this equality. I still don't know if it's true or not. So what can we do? We can multiply the left-hand side, the right-hand side, and if they are equal to each other, it means that everything has been done correct. That's what I usually do, actually. This is just, in my nature already. So let's substitute our matrix A. Matrix A was given to us. So 4, 1, 3, 2 times our vector E1. We just calculated it as 1 minus 3. And we just need to do this multiplication, which is supposed to be super easy for you, of course. So let's do it. So 4, we will end up having vector again. 4 minus 3 will be 1. 3 minus 6 will be minus 3. So this was A times E. You can see. What about it is equal 1 times E. So it means that this vector was found absolutely correct. So that's how I check my results, and that's how I recommend it to you. So you know that there are two checkpoints, sort of. The first checkpoint concerns this matrix or this system of linear equations. The two rows, which are always here, they should be proportional or even equal to each other. In this case, we had the equality of the rows. It means it's a good sign. It means that at least your lambda has been found correct. The next checkpoint is to check the components of your eigenvector. In this case, you can exploit this definition of your eigenvector. Maybe at first glance it seems quite annoying that so much checking is involved, but you realized after this one, I'm sure that it's better to spend some time on this checking. Okay, let's switch to the next lambda and repeat this process again, repeat this approach. So when lambda 2 is equal to 5, we need to take this matrix again in account and substitute lambda with 5. So 4 minus 5 will be minus 1, 1, 3, and 2 minus 5 will be minus 3. Okay, and I'm not going to even to write this times x1 like here. I'm becoming lazy. So let's discuss this matrix immediately. As you can see quite explicitly, these two rows are proportional. So the second row could be obtained for the first one by multiplying by what? By minus 3. So it means that it's redundant, and this is a good sign. It means that your lambda is equal to 5 is absolutely correct. So the next step is to find eigenvectors. Okay, let's try and calculate eigenvector. We need to rewrite this equation as an equation. So minus x1 plus x2 is equal to 0, which is actually equivalent to x1 is equal to x2. And of course, vector e2 will be super easy, 1, 1. It's just vector 1, 1. Okay, no, that's fine. So now it's time for checking. We need to check that if you multiply your A, matrix A, by this vector E2, it will be the same as lambda E2, 5 E2. So it should be the same. Put the question marks here so far because we don't know yet. Okay, let's rewrite our matrix A. Our matrix A is 4, 1, 3, 2. And let's multiply it by our current vector E2, 1, 1, and see what happens. So first row here and this column. 4 plus 1 will be 5. 3 plus 2 will be 5. As you can see, it's indeed, this is a vector 5 times 2. So it means that absolutely correct. So our assignment has been absolutely correct. So that's how I check my results, and that's why I'm always sure of myself. Even though sometimes I do commit some mistakes, as you noticed before maybe during my tutorials, but I don't take it too hard, because I know that there will be a way, there will be at least 2 checkpoints to correct my results. But now the most interesting part comes. What if you did make mistake? What should fall apart? Let's pretend that, for example, you miscalculated these lambdas. For example, typical mistake was to get minus signs between them, because if you look at this equation and try to guess factorization, some people might think that, oh, maybe it's lambda plus 1, lambda plus 5. No, it was one of the typical mistakes. So let's pretend that I got the wrong number, eigenvalue, minus 1. You could easily mix 1 with minus 1. Let's pretend. What happens then? It will be very interesting. So we are modeling the situation which some of you came across during exam. So you got the wrong answer, and you just not aware of this. You just push on. So the next step, you know that you need to calculate eigenvector. So okay, so what do we need to do? We need to take this matrix again and substitute lambda minus 1 here. What it will be? It will be 5 here. So 5, 1, 3, and here we will get 3. So I'll rewrite this here. I'm modeling this situation. So what happens? You need to look at this, have a closer look at this matrix and check if the rows are proportional or not. No, this time you can see that the rows are not proportional. It means that there was an error. So your lambda is simply incorrect. What does it mean? It means that you need to get back to the beginning and check your lambdas. So this sounds like a very good technique for, for checking your results. So I hope it was quite inspiring. And as well as for checking your lambdas, your eigenvectors, you already know this technique. If this definition doesn't work, so A times E is not equal to lambda times E, it means that you have another sort of error. You have an error when calculating your eigenvectors. Okay, so it is a sort of introductory example because it was too small. It was only 2 by 2. You might say that no, it's not ideal situation. Of course, you know the technique now, but it's better to give you a big example, more realistic example. So I decided to go over question 1b from tutorial 3 to demonstrate you the same technique of checking and one more technique of calculating, by the way. Okay, so in this tutorial, you're given matrix A. Okay, let's write it. -1, 3, -1 is the first row. The second one is -3, 5, -1. And finally, -3, 3, 1. And I think that the assignment was not only calculate eigenvalues and eigenvectors as usual, but also to build model matrix, expected matrix. But you know that this is not difficult at all to build these matrices. Once you have calculated lambdas and eigenvectors correctly, it will be just a piece of cake. Okay, so the most emphasis in this problem will be put on how to check your results. Are there any other ways to deal with these eigenvectors and so on? Okay, so the first task, as usual, first step is to calculate lambdas, our eigenvalues. To this end, we need to subtract lambdas from diagonal elements as usual. I'm not sure about my camera. It looks a bit, yeah, it looks a bit better. So let's start doing it. So -1 minus lambda, 3 minus 1. This is my first row in this determinant. So here I need to subtract lambda only from 5. So -3, 5 minus lambda, and the last one is -1. And the last row will look like -3, 3, and 1 minus lambda. And all of this should be equal to 0. But I'm going to, not to waste the space, I'm going to do calculations. Okay, so what is the best approach when you're calculating such big 3 by 3 determinants? The best approach is to find the row or the column which contains at least one zero. In this case, you will have to deal with less terms in your expansion of a determinant. But unluckily, we don't have such rows. So maybe we should go for the first row as usually. Okay, so let's try and expand along the first row. So -1 minus lambda, we need to cross out the row and column as usually and calculate this 2 by 2 determinant, which will be 5 minus lambda times 1 minus lambda and plus 3. So I'm finished with the first element. Let's move to the second element. It should be -3 this time. -3 times what? Let's cross out this corresponding row and column, and we will have -3 times 1 minus lambda, and -3, by the way, -3, not +3. And finally, the last term, or -1. I try to, because it's -1, I try to write +1. Okay, so we're crossing out the third column this time, and we will have -9 plus 3 times 5 minus lambda. Okay, so we are finished. And now we need to do some simplifications, but in a very clever, educated way, So it's better to not to expand it, not to do this multiplication completely. I mean that it's better only to do multiplication when it comes concerning these brackets, but not these parentheses. So it means that this guy gets multiplied by this guy, and that's it. So -1 minus lambda, 5 minus lambda, 1 minus lambda, and plus 3 times -1 minus lambda. So the best approach could be just to leave this term as it is, don't do anything to this. Maybe it will be wiser. Maybe you will end up noticing some beautiful factorization later. But as for these brackets, they should be expanded. But I'm going to do it step by step. So inside these brackets, you will have -3, -3. It means that it will be -6, and plus 3 lambda, 3 lambda. I hope this is correct. But even if I made already some mistakes, we do have this technique which we just discussed on the previous example. Okay, so what do we have here? -9 plus 15 will be 6. Okay, 6 and -6, so it will be -6. And here we have -3 lambda, but this sign gives us +3 lambda. Okay, okay. And now I'm rewriting this longest term again. Once again, I'm rewriting it. And I need to do the rest of the multiplication. So here we will get -3 lambda. Here we will obtain +18 -9 lambda. And there is no room for remaining two terms. -6 plus 3 lambda. So I'm rewriting this. guy once again. Y minus lambda 1 minus lambda, and it's time to find like terms. So let's find terms with lambda. So minus 3 lambda, minus 9 lambda, and plus 3 lambda. These two get cancelled out. So we end up having minus 9 lambda. Okay. As for constants, minus 3 plus 18 will be plus 15, plus 15 minus 6 will be plus 9. So we have this nice expression, and look at this. You can imagine that these are two terms actually. This is the first term, this is like a second term. And the second term is very nice actually, because if you pull out 9, just 9, you will end up having 1 minus lambda, which coincides with this one. So it means that we are on the right track. Let's write it once again, the first one. And here we decided to pull out 9. 9 times 1 minus lambda. And again, you can look at this expression as consisting of two terms only. Organizing my space here. So this is my first term, and this is my second term. They have a common factor, which is 1 minus lambda. And it should be pulled out. And here I'm drawing these brackets, my favorite brackets again. So 5 minus lambda and minus 1 minus lambda plus 9 is equal to 0. Of course. So we didn't need to deal with cubic equation. We were clever enough to make factorization. Okay, so the first term should be equal to 1. It means that lambda 1 is equal to 1. So we obtained our first eigen value. As for this expression, it needs to be multiplied. Okay, lambda squared, or there is a chance to make mistakes here. So it will be minus 4 lambda, I suppose. Minus 5 plus 9 will be 4. This is correct. And maybe you immediately notice that this is so-called perfect square. It could be rewritten as this, and which gives us lambda 2, 3 is equal to 2. It's not necessary to write it down like this. This is just my habit. Because we were sort of expecting 3 lambdas, 3 different lambdas. But it happens so that these 2 lambdas just coincide. You can just say that you have 2 lambdas. But mathematicians prefer to say that no, we have 3 lambdas, but just 2 of them are repetitive, like repetitive roots. So they just coincide with each other. Okay, so we did get our lambda. And by the way, it's time to write down our spectral matrix. This was our assignment. Some people were unclear as to what to do in these situations when you have two equal lambdas. So the first lambda was 1. That is why the first column will be 1, 1, 1, 0, 0. The second lambda was 2. So this is column. And the third lambda is 2 as well. That is why your spectral matrix look like this. No problem with these repeated values. Not at all. That is why maybe it's a good approach to write them not just lambda, but lambda 2 and 3. To emphasize that these are just 2 different lambdas, or 2 lambdas, but they just coincide. Okay, so there's nothing new for you actually here. And it's time to discuss more serious things, because we need to be able to check our results, because who knows, maybe I already made a mistake without being aware of this. So let's switch to the second step. So now we need to calculate eigenvectors corresponding to each of these lambdas. Let's start with the first lambda, which was 1. It was 1. What do we need to do? We need to go one step back. Do you remember this matrix where you have lambdas for the first time? So this is our matrix. And we need to substitute lambda with our current value. Our current value is 1. So here we'll have minus 2. So the first row will be minus 2, 3, minus 1. Okay, minus 2, 3, minus 1. Then minus 3, 5 minus 1 will be 4. So minus 3, 4, minus 1. Minus 3, 4, minus 1. And the last row, minus 3, 3, 0. Minus 3, 3, 0. So that's how our matrix looks like. And of course, you need to calculate your eigenvector. You need to multiply this by x1, x2, x3, and set it equal to 0 vector with 3 components. But you know what? You usually just write down this matrix and start dealing with it. You know, unlike in the previous example, which was about 2 by 2 matrix, you can't immediately detect a mistake in your lambda if there is a mistake here. You need to bring this matrix to row echelon form in the first place. And only after this, you can make some conclusions if my lambda was correct or not. That is why you need to have some patience. But you know what? I think it would be, let's just rewrite our matrix here. And now, you know, I decided to actually to kill 2 birds with 1 stone now. Because the main objective of this tutorial, as I said before, was to teach you how to analyze and find your mistakes, if there are any. But the second aim will be to teach you one more technique of how to bring your matrices to row echelon form, because so far it seems that you have been restricted in your methods, but now it's time to become more advanced. Look at this. What is so bad about this situation? You know, we are quite used to the fact that we always had 1 here, right? Because 1 is a very convenient number. It would allow us to get rid of these guys immediately by multiplying the whole first row by some convenient constant. But unluckily, we have -2 here. And moreover, 2 and 3, they just don't have a common factor. And that is why it looks like very annoying. What do we need to do here? Just some obstacles, some arithmetic, some very simple arithmetic, but at the same time, it sounds like an obstacle. You know what? It's time for you to learn one more technique. Let's call it method 1. Let's call it method 1 because I don't mind spending more time. Okay, method 1. Method 1. I don't mind spending even more time to go over these 2 methods. Okay, so what is method 1? Method 1 is to notice that you have nice numbers here in the 3rd column. And maybe you said, it's such a pity that the 3rd column is not the 1st column, actually. And maybe you remember that back then, when I was telling you this material related to this tutorial, I told you that you are allowed to manipulate rows, but it's not a good idea to manipulate columns. So I told you that it's not a good idea to swap the columns. But you know what? I think that quite a lot of time has passed since then, and you are ready to digest new technique, as it were. So let's swap these columns, actually. Let's swap. There's nothing bad about it. Provided that you are quite attentive. You know what happens? You know that every column, the problem is, why I didn't recommend you to do it before, because every column corresponds to its own, variable. So this column was about x1, x2, and x3. And what happens if you swap the columns? These values get swapped as well. That is why there's nothing bad about swapping columns. So I'm swapping the 1st and the 3rd column, but you need to remember this fact. So let's try and write them down. So this will be x3 this time, and this will be x1. It's very handy to write down this to keep them writing all the time, because you will not forget about it when you are ready. And now it seems like it's very easy, very convenient to bring this matrix to row echelon form. In the first place, I'm tempted to multiply the first row by -1, because it's always better to have 1 here. So let's do it. Let's multiply the first row by -1 to get our usual 1 here instead of -1. But as for this guy, it could be deleted immediately. If you multiply the first row by -1 and add these 2 rows together, we will get 0 here. This is our first objective when we are dealing with Gaussian elimination. Okay, 1 plus -1 will be 0. -3 plus 4 will be 1. 2 minus 3 will be -1. And we don't do anything with the 3rd row because we already have 0 here. Okay, and let's just keep writing this because it's very, dangerous to forget about it. Okay, so what we do next? We need to get rid of this guy. We need to turn it into 0 by means of the previous row. Okay, so it means that we can rewrite the first 2 rows. 1, 0, 1, -1. And to get rid of this guy, -3, we should multiply the second row by -3 and add the result to the 3rd row. So -3 plus 3 will be 0. And here we have, what is this? I made a mistake. It looks like I did make a mistake. Yeah. Because it should be Okay. It's actually a very good idea that I made a mistake. Oh, I didn't even expect it. Look at this. You know what I was going. My first intention was to imitate the mistake. My first intention was to present you the correct solution, and after that to imitate this mistake. But you know what happened? It happened so that I made the mistake from the very beginning. So what does it mean? So if your lambda was correct, or if your transformations were correct, it would mean that one of the rows, at least one of the rows, would turn into zero row. You know what I can see now? We have no zero rows here. It's a very bad. It's an indication that there was a mistake. Maybe it was a wrong lambda, and maybe it was a mistake in our transformations. I think it was a mistake in my transformations. I think that I had to get -3 here. Let's get back. I made a mistake somewhere. I don't know, no idea. So 3 minus 3. Maybe when I was trying to get rid of this -3 here, I made a mistake. So what? Let's analyze what I did here. I can't find mistake. It should have been -3 here. Yeah, of course. I was just rewriting this third row, and I didn't rewrite it correctly. That's it. So it was quite a laughable mistake, but nevertheless. So we should end up having 0. So now you witnessed this realistic, situation. So I did make a mistake. It was just a careless mistake, but nevertheless, I immediately spotted a mistake because I know from my previous experience that in this resulting row echelon form matrix, there should be at least 1 0 row, and there was none, 0 rows. I immediately realized, oh, no, I made a mistake. Maybe it was a wrong lambda, maybe it was a wrong transformation. Luckily, we managed to find the mistake immediately. So now I actually demonstrated you how to find your mistakes immediately. In this resulting matrix, let me repeat it again. In this resulting matrix, there should be at least 1 0 row, sometimes even 2 0 rows. Okay, and what was our technique? What was our proceeding step? So you need to find these leading elements for each row, and then you switch to the columns. And the column which doesn't have any leading elements, it should be called free variable. In our case, it's look at this, look at this. I was about to make another mistake. And this is the right time to recall that the last column was corresponding actually to x1. That is why our x1 is free variable, not the x3, because we swapped the columns. Okay, x1 is equal to 2. And now we need to rewrite the first 2 rows as equations. So x1 minus 3x2 plus 2x. Made a mistake again. Look at this. X3, and this should be x1. And the second row looks like x2 minus x1 is equal to 0. I'm always tempted to do the same mistake, which I'm discussing now, but because it's it's like an instinct. Okay, so the second equation. In the second equation, let me move here. So instead of x1, we need to substitute t and maybe to move it to the right-hand side. So x3 minus 3x2 is equal to -2. And the second equation will give us x2 is equal to t. So we already have x2. x2 is here, x1 is here, and we need to calculate x3. Let's just express it first. So 3x2 minus 2t is equal to 3t minus 2t, which is again t. So our x3 is equal to t as well. I need to take a new page now. So what do we have now? We have our solution is x. Do you remember the solution of the system of linear equations should be presented like this: x1, x2, x3. So our x1 was free variable, and we denoted this as t, and the remaining variables were t as well. We pull out t, and we end up with this 1, 1, 1. This is our first eigenvector, 1, 1, 1. So. And now it's time to check. Maybe we could easily make a careless mistake, just solving this problem. Everyone would agree. I myself tried to make this mistake, by the way, just in front of your eyes. So it's better to do this checking. Maybe it will take us like 10 seconds, 50 seconds, even more, but it's always a good idea. Okay, so this in this case, you need to use this definition of eigenvector. A times E1 should be equal to lambda 1 times E1. Lambda is equal to 1 in our case. So Let's try and do it. So where's our matrix A? I already lost my matrix A, to be honest. Yeah, here it is. -1, 3, -1, -3, 5, -1, -3, 3, 1. So this was my matrix A, and times my vector E1, 1, 1, 1. So I'm calculating the left-hand side of this equation. Okay, let's do multiplication. Super easy. So -1 plus 3 will be 2, 2 minus 1 will be 1. Okay, the second row. -3 plus 5, 2, 2 minus 1 will be 1. Nice. And the third row, -3 plus 3, 0, 0 plus 1 will be, as you can see, it does equal to 1 times E1, sorry. Yeah, so it means that it's absolutely correct. At least the first vector corresponding to lambda is equal to 1 is correct, which is good news. And as you can see, I didn't even need to imitate my errors. I committed errors already, which is actually very good. I'm really happy that I committed this error, because you could witness how this process of detecting errors happens. So it's better to learn from mistakes, actually. It's a common wisdom, as we know. Okay, but now I wanted to give you a second method. Let's get back. Don't rush to the next lambda. I just want to discuss with you what is the method 2. So we encountered quite, how to say, uncomfortable situation, if I may say so, that when we don't have a 1 or -1 here, it's rather uncomfortable to bring the whole process of bringing these metrics to the raw echelon form. What is the second technique? Let's discuss it. Maybe some other people would prefer the second technique. So let's write down method 2, and let's copy this situation here. So we need to bring this matrix to row echelon form, but the matrix is not very good, not very convenient for us. What can we do with this matrix? Of course, maybe some of you noticed that if you divide the third row by 1 or -1, you immediately end up having 1 or -1 here. You can swap the rows and so on. But let's pretend that you didn't notice it. What is the general approach to this not very comfortable situation that you have 2, 3, 3, nothing common with these numbers? You know what? But the only thing which annoys me, there are too many minuses here. Let's just multiply every row by -1, because it doesn't look nice to my taste. So let's do it first, and then we can discuss it. So 3 minus 3, 1. Remember, I didn't notice that this row can be divided by 3. I'm just decided to get rid of these guys by means of the first row as usual. What can I do with these numbers? Some people prefer to get 1 here by dividing the whole row by 2. But it's not a good idea, because you will end up having factors. So this guy will be 1, of course, undoubtedly. But this one guy will be -3/2, -1/2, and so on. It's not a good idea to deal with factors, to my taste, to be honest. You still can do it, but I wouldn't recommend it to you. You will immediately make a lot of careless mistakes, I'm sure. So it's better to use the following technique. You have 2 here, you have 3 here, and you need to get rid of this guy. What can you do? You can actually do the following thing. You can multiply the first row by -3, okay, and the second row by 2. And you will have here you will have the result -6, here you have +6, and you will have this 0, as you notice. Of course, you should be more concentrated compared to what we did before, but I don't think it's a big issue for you. Okay, so -6 plus 6 will be 0. Here, -3 by -3 will be 9. 9 minus 8 will be 1. Then you have -3 plus 2 minus 1 here, and that's it. That's it. And the same technique could be applied to this guy. Let's pretend that we didn't notice. We still don't notice that this could be 1 minus 1. Let's do the same. We need to multiply the third row by 2 now. So -6 plus 6 will be 0 again. 9 minus 6 will be 3. -3 plus 0 minus 3. So this is the second technique. I would recommend it to you. Maybe some people say that, oh, it's quite tough to multiply this row and keep everything in mind. You are not allowed to write here because it's going to be a big mess here. But it's not so difficult for you. You're university students after all, not school children. Okay, so we did perform our first step. And then remember, our objective is to bring this matrix to row echelon form. So we need to get rid of this guy. in the third row by means of the second one, but we already did this before. We need to multiply the second row by -3, and in this case you will end up this way. So you have quite a big choice of methods now as to how to bring matrices, 3 by 3 especially, matrices to row echelon form. The method one was that you are still allowed to swap columns now, but remember that you need not to forget about it, because otherwise it will be absolutely incorrect. The second method is to manipulate with these numbers if they are not very comfortable, even if you don't have one here. But there are many possibilities as well. For example, in this case, in this example, I pretended that I didn't notice that I could have obtained one in a much more easy way. So just by dividing the third row by 3 or -3. Okay, so you're pretty familiar with all these techniques now, and I think it's better to finish. So I already informed you of everything I intended to, but nevertheless, let's finish this task, this question 2, question 1b, because I think it's better to finish our task, even though you already know everything, but I don't mind spending more time on it. So we need to deal with our lambda, which is equal to 2. Let's do it. Let's do it because it's quite an interesting situation. So what do we need to do? We need to find the eigenvector, or vectors maybe, I don't know, corresponding to this lambda is equal to 2. Again, we need to go back to this matrix with lambdas and substitute lambda with 2 this time. So we have -3 in this case, -3, 3, -1. The second row will be -3, 5 minus 2 will be 3, 3 minus 1. And the last row, -3, 3, 1 minus 2 will be -1. I hope it's correct. Yeah, it looks very strange, this matrix, too symmetrical, but it's a good sign, I think. Okay, what can we do next? I don't know. You know what? I think that these minuses are really annoy me. I always tempted to change the sign to get as few minuses as possible. So it's just my personal maybe annoyance. I don't know. And immediately after that, you realize that even though you don't have one here, it doesn't matter. What matters, what really matters in this example, that you can see that if you start uh, eliminating these guys, applying our usual technique, so by multiplying the first row by -1 and adding it to the second row, you immediately get the whole row of zeros. And the same applies to the third row. So we already got this row echelon form prematurely, I would say. And you know, this time we have even 2 zero rows. It's a very good sign again, as you said. The only situation which is indication that you have made a mistake if you don't have any non-zero rows at all. It's a 100% indication that you made a mistake. But in all the other cases, when you have at least one zero row, it's a good indication. It means that your lambda is correct. Okay, so it's time now to find eigenvectors. So how can we do it? We need to find leading elements. We have only one leading element, by the way. Yeah, and that is why we have 2 columns which don't have leading elements. The second and the third columns. It means that this time we have even 2 free variables. In this case, we need to use letters T1 and T2. We have 2 parameters now. Very unusual case. Maybe you already forgot how to deal with this. Okay, and now we need to switch back to the system of linear equations. It's not going to be a system, actually. It's just the first remaining equation. 3x1 minus 3x2 plus x3 is equal to 0. So that's how the first row gives us the first equation. We need to substitute our results, our notions here. Or maybe it's better to express 3x1 first. X1 is 3x2 minus x3. And here we can substitute our parameters. So 3t1 minus t2. And finally, we need to express x1. So 3t1 minus t2 should be divided by 3. Maybe it's better to rewrite it in this form. T1 minus 1 over 3 times T2. So we already have all our variables here, here, and here. And it's time to start manipulating the whole solution of our system. So solution should be written as x capital, which is column of our variables x1, x2, x3. And now we need to substitute our results. So x1 is equal to this, t1 minus 1 over 3 t2. x2 was denoted as t1, and x3 was denoted as t2. So this is very interesting situation. And now, as you may remember, we need to split this column into two columns. The first column are coefficients in front of t1, and the second column will be written as coefficients in front of t2. And let's go over this column. So in the first row, t1, you can see t1. It means the coefficient is 1 times t1. In the second column, again, 1. And there's no t1 in the third, not column, sorry, in the row. It means that the coefficient is just 0. Okay, so the same reasoning could be applied to the third, to t2. You have a coefficient minus 1 over 3, 0 here, 1 here. So as a result, you have this. This is vector e2. We already used notation e1, do you remember? And this is vector e3. So these are two eigenvectors. So eigenvectors corresponding, so we have lambda is equal to 2. Let me remind you. And eigenvectors are e2, which looks like quite nice, 1, 1, 0. But e3 doesn't look very nice, to be honest. These fractions are always very annoying. What can we do with this vector to improve it a little bit? We can multiply every component by 3 or even minus 3, which you prefer. Let's multiply it by minus 3. Then they all become integers. So the first component will be just 1, the second will be 0, and this will be minus 3. So this eigenvector looks much nicer, of course. So this is our result, but remember, the objective of this tutorial was to teach you how to check your results. We are not quite satisfied with this result until we have checked it correctly, okay? And you know how to check it. Let's check them both. Maybe I organize two columns here because my camera looks like this. Yes, so I'm going to check. So lambda is equal to 2. I'm writing here. So now it's checking. The last step is checking. So I'm writing my E2 here so that I don't need to use my previous page. And E3 is here, 1, 0, minus 3. And I'm going to check it. So A times E should be lambda times vector itself. I'm going to check this equality. Maybe for some of you it seems like quite a long and annoying process, but it's absolutely necessary, as I can see, because I suspect that many of you were very frustrated with your results from test 1, because the only mistake you made was just some careless mistake in calculating these eigenvalues. So I think it's quite absolutely worth it. Okay, so I'm going to calculate this left-hand side. So matrix A should be copied from my previous pages. Matrix A look like this in our minus 3, 5, minus 1, minus 3, 3, 1. And now I'm going to multiply it by this vector E2 this time. 1, 1, 0. Let's do it. It's quite a simple operation. Okay. Let's start with the first row. Minus 1 plus 3 will be 2. 2 plus 0 will be 2. The first component is 2. Then the second row. Minus 3 plus 5, 2. 2 minus 1 will be 1. And the last row. Minus 3 plus 1, 0. So what about the right-hand side? Right-hand side will be 2e2, but this is the same as the result we just obtained. Look at this. No, look at this. 2, 2, 0. No, I made a mistake. Very good. I didn't even need to imitate anything for you. I just made a mistake myself. So what was my mistake? Maybe the mistake was when I was calculating eigenvector, or maybe I just made a mistake here. There could be many mistakes everywhere actually. I need to check my result. So 1, 1, 1 was correct actually. 1, 1, 0. I just need to consult my notes just in case. It looks like cheating, but nevertheless, I think that I did some mistake. Maybe I copied matrix A incorrectly. Let's have a look at this. Minus 3 minus B. No, it was correct. So multiplication maybe went wrong. With the second row, I think. Minus 3 plus 5 will be 2. 2 plus 0 will be 2, of course. I remember saying 2, but writing 1 instead. Okay. So as you can see, you can make mistakes everywhere. And now they coincide. It means that this vector is absolutely correct. Okay, we are quite happy. But let's check this vector as well. So again, we need to check the first, the left-hand side of this equation. Again, let's copy our matrix A from here. -1, 3, -1, -3, 5, -1, -3, 3, 1. And now we need to multiply it by this vector, 1/3. Okay, it's better to write it here. Okay, first row, -1 plus 0 plus 3 will be 2. 2. The second row, -3, 0, plus 3, 0. -3 will be -6. Okay, so this is left-hand side. A times E. What about right-hand side? Right-hand side should be 2E3, which is 2 times our vector 1, 0, -3. It will be just the same result, 2, 0, -6. It means that everything is absolutely correct. So that's how you should have found errors in during your test. Of course, you might say that you always have this time pressure during test. Of course, it's true, absolutely true. You get nervous. You are tempted to to neglect this step, this very crucial step. But I think it's actually worth it. So just remember about it during your exam, which is going to be in June, as you know, because there is a chance that you will get given quite similar task in this game. I forgot to make the remaining thing. The assignment was to write the model matrix, right? Model matrix. But you know what? What is the issue with model matrix? Of course, this is a matrix whose columns are our eigenvectors, but you need to check that the eigenvectors are given in the same order as you give lambdas in your spectral matrix. That is why let's copy spectral matrix here. It's very important as well, because in linear algebra, as you know, order does matter. So let's copy our spectral matrix here first. 0, 2, 0, 0, 0, 2. And now we can discuss our model matrix M. So you can see the order. The first column is about lambda is equal to 1. That is why the first column here should be only the first vector corresponding to this. It was 1, 1, 1, as I can remember. As for the remaining two columns, column 2 and 3, they are all about lambda is equal to 2. And you obtained two eigenvectors corresponding to lambda equal to 2. In this case, you can give them in any order, actually. You can give them this vector first and the second vector here. But also, you can swap these two columns, no problem. So different students could have obtained different results, and they will both could be true. As well as vectors themselves. Do you remember we discussed it earlier? Remember we discussed it many times. Even the vectors, eigenvectors themselves, are not unique. For example, the most common result is 1, 1, 1, of course, because people prefer smaller numbers. But some of you could have given result like 2, 2, 2, and you would have been absolutely right. And I wouldn't have dared to tell you that no, it's not correct answer. It would be correct as well. Okay, so that's it for today. So, bye-bye.